Resistances in series and parallel. First, we'll consider resistances in series. So we have a battery here which is driving a current I through three resistors R1, R2, and R3, all of which are in series. Series means they are connected end to end. Now, because of this arrangement, the same current I has to flow through all three resistors and get back to the battery. So you can think of the battery as a pump raising the potential of charge, which then drops down through each of the successive resistors R1, R2, and R3 like a series of waterfalls. The potential drops from A to B to C to D. From Ohm's law, we know that the potential drops are VAB, that's the potential drop across the resistor R1, is simply the current I times the resistance itself, R1. Similarly, the potential drop VBC across the resistor R2 is I times R2, and so on. VCD equals I times R3. So the total drop, we have to add them if you want to know what's the potential difference between A and D, which is the same as the voltage V of the battery. That's equal to VAB plus VBC plus VCD. And if we can substitute Ohm's law into each one of these components of the voltages, we get the relation here, which we will write as I times an R, which is the R total resistance. Therefore, R total simply is the I cancels out on both sides of this equation, and the total resistance is simply R1 plus R2 plus R3 for a series combination. Now for resistances in parallel, the situation is a little bit different. So we have three resistors, R1, R2, and R3, like a ladder, parallel rungs of a ladder. And the same battery is driving some current I, and that current I has to distribute itself between the three resistors. So when it comes to this junction here, part of that current goes through R1, part of the current goes through R2, part of the current goes through R3. And the total current I is simply the sum of I1 plus I2 plus I3. Now, however, the voltage drop across these resistors are all the same because they're all connected to the same battery. So we can write down this relation that V equals I1 R1 equals I2 R2 equals I3 R3. And again, we'll define the equivalent resistance. So suppose we want to replace all of these three resistors with one resistor, which we call as R equivalent. What would it be? Now, we can state I equals I1 plus I2 plus I3 and substitute for the individual currents from this equation over here. So I1 is V by R1, etc. And we write that as V by R equivalent. So there should be R equivalent here, and giving us the relation that 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. So the resistors in parallel add inversely to give you the equivalent resistance. Now, one fact to remember here, which is not proved but something stated, is that the equivalent resistance is always less than the smallest of all the parallel resistors. Now, there are two useful relations that you can keep in mind. One comes from the series combination. The other comes from the parallel combination. The series combination gives you a very easy to remember equation for a voltage divider. If you look at the circuit on the right hand side, what is the voltage at the point B with respect to C? I call that as VB here. This is VBC. That simply is equal to the battery voltage times R2 divided by R1 plus R2. So let's see how that works. So if this resistance is very large compared to R1, then most of the voltage drop will occur across R2. So if R2 is very, very large, I can neglect R1, and the voltage at B is simply the total voltage V. On the contrary, if R2 is 0, then of course the voltage at B is the same as the negative voltage, negative terminal voltage, which we take as 0. So therefore, when R2 is 0, the voltage at B is 0. So that works out. In a similar manner, you can construct an equation for a current divider. So here I gets divided into I1 and I2, and you could write I2 as the total current I times R1 divided by R1 plus R2, because it's the other resistor which comes into play. So if this resistance is very large, then you can cancel R1 on both sides here, and your I2 will be equal to I. So what that means is that if this is very large, the current would rather go through R2 rather than to R1. On the other hand, if this resistance is very small, if this is 0, then I2 will be 0. The current would rather go through R1 than go through R2, so therefore I2 will be 0.